All right, we have one more presentation next up on our agenda before the next break. We have Marc Solé of the Barcelona Supercomputing Center presenting a demonstration of SPARROW, a low-cost SIMD unit for AI acceleration in space processors. Marc, it's all yours.
Hello. So yeah, I will talk about SPARROW. I will do a brief demo. This project has been my master thesis, and I aim also to work with it in my PhD. So as a bit of context, in the recent years, we've seen an increasing interest in artificial intelligence and machine learning. And that happens in different fields, but also in the space domain. As an example, we can see the Mars rover, the Perseverance, that uses artificial intelligence for pathfinding, and also some missions from the European Space Agency, such as the FSW or the OPSAT, that use artificial intelligence for cloud removal from images in space. However, the existing space processors cannot keep up with the requirements of these applications. And what we would do in Earth's surface is the use of commercial devices, such as GPUs or accelerators. This cannot be done easily in space due to these SCOTS devices do not provide radiation hardening and therefore cannot be safely used beyond low Earth orbit. And also they do not have space qualified software stacks and lack support for real-time operating systems. Our alternative has been designed for two space processors, which are the Leon 3 and Noel 5. And it's a low-cost unit which aims to speed up artificial intelligence applications. The design of this module has been done after analyzing the most common operations found in machine learning workloads. And the architecture resulting is a single instruction multiple data, similar to other approaches such as AMSIA. However, we introduce a feature that allows us to reduce the hardware overhead, which is the reutilization of the integer register file. This forces us to work with 8-bit integer values. However, the literature shows they provide enough precision for machine learning inference. This SIMD within a register approach is also combined with some embedded GPUs features, such as saturation, and the encoding of the most common values in 5-bit immediates that fit within the instruction. The addition of the module in a processor requires minimal hardware modifications, and this simplifies the process of qualification for space, allowing the use of incremental qualification. Also, since we do not modify the already existing hardware, such as the pipeline, we can reuse the software without needing to requalify that, and only the software that introduces SPARROW instructions will need to be qualified again. Also, it works without requirements of real-time operating systems and does not has any impact in the context switch times. The architecture of the module is divided into two main stages. As you can see, the first stage is used for parallel computing with a higher precision vector that holds this value, avoiding any kind of precision loss due to working with 8 bits. Also, this stage takes a single cycle, and this allows to do complex operations such as multiplication without requiring any additional cycles. In the second stage, we also take only one cycle, and in this case, we perform reduction operations such as sum, finding the maximum or the minimum. Furthermore, we have increased the SPARROW with other features such as a mask or reordering and replication using a Swiss-Link network, and this is controlled by the SPARROW control register that can be accessed as a special register. The SPARROW has been implemented in the Leon 3, which has been synthesized on the Xilinx Ultrascale Plus FPGA. The addition of the module did not any impact in the clock frequency, which has been kept at 100 MHz. And also the fraction, just a fraction of the hardware overhead compared to other vector processors. We only require a 30% increase of resources, whereas other approaches take up to twice the size of the base processor. Also, some preliminary implementations we've done with the Noel 5 show that we have a 5% increase of resources for a Linux-capable processor, whereas 13% when using the smallest possible configuration. You can see in this plot the resource utilization of LUTs with SPARROW in the Leon and just the Leon in both scenarios with catch and no catch. Also, some space FPGAs provide radiation-hardened LUT RAM, but they do not provide such protection for the VRAM, which is the one we used. And therefore, we tried to do some synthesis with the VRAM disabled in order to force the use of LUT RAM. We have seen in this case that we have 16% to 25% of hardware overhead. And again, you have here the plot with the LUT utilization. So we are working with two different architectures, with Spark for the Leon 3 and RISC-V for the Noel 5, and therefore we had to adapt the instructions. However, many of the fields are common, and this is not such a difficult process. We do need to increase the two new fields, which are the first stage operation code and the second stage operation code for SPARROW. And these two fields are independent and can be combined with different options in order to generate up to 200 different instructions. In order to take advantage of these hardware modifications, we implemented software support for GCC and LLVM in terms of assembly. The performance achieved for both compilers is pretty similar, and the programming looks like SIMD Intrinsics, thanks to the use of C-inline assembly. We will later see an example of how this works. In order to find the names for each instruction, we decided to combine the operations of both stages joined by an underscore, but for certain instructions we required an alias, such as dot instead of mul sum for the dot product. Also, we can use prefix S for saturation and prefix U for unsigned. Furthermore, we have added support to the existing read and write instructions in order to access the SPARROW control register. To further simplify the programming, we have created a lightweight library, which is being written in C preprocessor macros, and that it's used to hide the use of inline assembly. Also, we included a variable to control the SPARROW control register value, and therefore reducing the complexity. We will also see how this affects the programming in the example later. In the table below, you can see all the functions we have implemented in the library and the description of what they do. So for the programming, here we have a comparison on how it looks with using C-inline assembly and using the SPARROW Intrinsics library. The first thing we can notice is how we can set the SPARROW control register. On the left, we had to set the value with an hexadecimal or with decimal, but we need to know exactly how this register is organized and which values are the default ones. However, on the right, in the SPARROW Intrinsics library, this can be done with different steps in order to set each one of the fields. Finally, in line 10 and 11, we can see the commit of this modification of the SPARROW control register, which is the same but more user-friendly on the right. Also, in the line below, the 15 in the left and 16 on the right, we see a node. This line is necessary in order to have a 3-cycle latency between the setting of the SPARROW control register until it's used. And this can be hidden by just reorganizing the code in a way that we can make sure that there are 3 cycles between this setting and using of the register. Also, another feature we can find is how we access the 4 bytes of the vector. And this is done using a word pointer, allowing us both to read and write the vector as a simple word, even though we are working with 4 bytes. Finally, we see the line which corresponds to the actual SPARROW instruction. We can see that thanks to C-inline assembly, we can pass the variables into the assembly and let the compiler handle the allocation of the variables. However, we can see also that on the right, the code is more user-friendly and it's easier to understand and to write. Now we'll move on a more practical example for the matrix multiplication, which is one of the essential building blocks for neural networks, both for fully connected and convolutional layers. In this case, we have decided to initialize the matrices at random, but using a known seed in order to allow reproducibility. In this case, also we have initialized matrix B as transposed, and this is done in order for, when loading the data into the vector, to access it as rows instead of columns, which simplifies the loading, like in the example I showed before, as with a pointer. Also, in this case, we use saturation, which is by default in SPARROW simply done. However, in the CPU version, we did that using conditional assignments in preprocessor macros. Finally, you will notice that on lines 4 and 15, we have set some labels. These are used later in order to time the execution of the program. Here we are now seeing an example of the execution. In this case, we are using GRMON, which is a tool provided by Geisler in order to access the Leon 3 on the FPGA. And it allows us to load a program and debug it how we want. We can see that in this case, we have loaded the 8x8 matrix multiplication for the CPU, and it's now loading the SPARROW version. We can see that in both cases, the program has terminated correctly, and we can check that the output is the same in both cases, proving that SPARROW works as we intend. If we move now on measuring the performance of SPARROW, first we do a 64x64 matrix. In this case, we are using the same GRMON, loading this time the 64x64 matrix. Now you can see here, I'm setting the breakpoints. We mentioned it before in the code. This will allow us, when the program hits those, as it has just happened, we can set a counter in order to time the execution of just the part that interests us, in this case, the kernel of the matrix multiplication. And when we print the results of the execution, we can see the number of cycles that it took. Also, the program has exited correctly, but in this case, we have disabled the print because of the size of the matrix. We've seen that the CPU took approximately 7 million cycles. If we check now for the SPARROW version, the process is exactly the same. Once again, we set the breakpoints. Okay, and the execution has hit the both breakpoints has finished, and we can see the result of execution cycles. We had approximately a little more than 400,000 cycles, and this means that we had over 16 times the speed up, which is a great result for SPARROW. Now we will do the same test for the 512 matrix size. In this case, we will see that the execution time is considerably larger, but also it will allow us to see more clearly the benefits of SPARROW. And now you will see that the execution actually takes some time, and we can feel this by the wait. Bear with me, it's just a few seconds. Okay, and the execution has finished, and we will now see that the number of cycles is much more than what we had before, and this is due to the increase of the matrix size. If we check now the same with SPARROW, we will be able to see the difference in execution time and also the benefit of using SPARROW. And yeah, that's it. As you have been able to see, the difference is dramatic, and it's a huge point for SPARROW. We've seen that in the first execution in the CPU, we took almost 4 billion cycles, whereas in SPARROW, we only required almost 400 million cycles. And this means we had over 10 times the speed up, which is less than in the previous scenario, but still is a great result. So the reason why the speedups are higher than 7 times, which is the theoretical maximum that can be achieved with SPARROW, is due to the saturation. In SPARROW, saturation has no impact on the execution time. However, this is not true in the CPU version. As I said before, we are introducing this saturation using conditional assignments. You can see in this graph below the results when the saturation is disabled for different sizes, and we can see that the speedups are more moderate, around 3. However, for some particular sizes like 64x64, we see that the speedup reaches almost 6 times. Also, you can compare the differences between GCC and LLVM, which is mainly the same, excepting some cases. Other tests we have performed is a grayscale conversion, which has been done by just dividing by 2 each of the color components of a pixel. This division has been done by a shift in our case. And then we proceed to add them to obtain the gray color. And also the results shown below provide a speed up around 3 times. Which are close results to what we had in an edge detection filter, which is actually like a convolution. And in this case, also we took advantage of the mask in SPARROW, as it allows us to trim the values which are left outside of the matrix, and also to reduce the number of the size of the kernel to 3, which is also a limit, in the maximum performance of SPARROW, as it can compute up to 4 values at the same time, and we had to reduce this at 3. However, the results we achieved for all the tests are similar to other vector units for the same tests, and we took just a fraction of the hardware overhead, as I mentioned before. Also, we have tested SPARROW with a more complex inference application based on Cypher-10 from the GPU for Space benchmark. This inference application takes multiple layers and as input 32x32 images, and the speedup achieved are over 5 times, which is still a great result. We have also performed the same tests for Noel 5, in this case in simulation, and the results we have achieved are pretty similar. So as conclusions, we have presented SPARROW, which is a low-cost SIMD module, which has lower cost compared to other traditional vector processors, and also is specifically designed for machine learning acceleration. It has no impact on the clock frequency and is portable among different designs and architectures. Also, it can provide high performance for inference applications, and we have provided software support similar to SIMD Intrinsics to work with it. As future work, however, we would like to complete the software support in order to provide compiler code generation and also support for known frameworks such as TensorFlow. Also, we plan to do some evaluations under RTEMS with space-relevant machine learning benchmarks, which are currently under development at the European Space Agency in the OBPMAC project. And also, we would like to test it in orbit using ESA's OPSAT FPGA. So, as additional information, I would like to mention that this project is open source, both the hardware and software implementations. And all the code will soon be uploaded in the repository you can see here. You can also access it using the QR at the right. Also, we would like to mention that the project was the winner of the Xilinx Open Hardware 2021 competition in the student category. You can also check the repository in their web page. And also it was awarded as the best master thesis project by the Spanish chapter of the IEEE AESS. Finally, I would like to mention that the paper has been accepted at date 2022, which will be presented in next month. I would like to thank all the organizations and agencies which partially have funded this project. And thank you all for your attention, and I'll be happy to answer any question.
Thank you so much, Mark. We have about 5 minutes for some questions coming in. First one from Joel Sherrill at OAR. Does SPARROW have registers or state which would need to be managed as part of context switches?
So the only state that it's worth keeping is the SPARROW control register, which must be handled by the compiler or by the user at the moment, but we plan also to make this automatic in order to have more easy programming for the user.
Okay, great. Give another minute or so for any other questions to come in. Next question is how to collect floating point exceptions in case they happen.
Well, as I mentioned, SPARROW works only with 8-bit integers, so we don't have any kind of exceptions because the only possible exception would be division by 0, but we do not provide division at the moment. So we don't have to worry about exceptions at all.
Okay. All right. Give just another minute for any other questions to come in. All right, Mark, thank you so much for your time today. One more question just came in right at the very end. For the Git link you gave doesn't seem to be publicly accessible yet.
Yes, the link will be made public soon. In the next days, it will be made public. But if you want to access what we have at the moment, you can see the repository, which is shown in the Xilinx Open Hardware competition. Okay, great. Thank you so much, Mark. Thank you. Goodbye. And yep, thank you.